All right, everybody, welcome back to another wonderful day. Thank you so much for being here and being on time. Today, we are going to be working on pandas. So we've talked for the past week or two, we've been talking about pandas and data science and NumPy. Well, really what you've seen, and hopefully you watched the lecture, really what you've seen is that everything is built on top of each other, right? So we're using Python as our base programming language. And on top of Python is NumPy. NumPy is built to work with arrays and list type objects. And then on top of NumPy, we've got pandas. And pandas basically just adds fancy tags and labeling to data to make it easier for us to work with. So today we're going to go through the basics of how to work in NumPy. Now, before we get there, we are going to start. Actually, I'll stop. Does anyone have any questions over the lecture before I continue? Okay.
No questions.
No questions. Perfect. Okay, so today, like I said, we're going to start with pandas for data science specifically. Real quick at the top, like I was telling you guys in my lecture, I always put a data checklist at the top of my data science forms, and quite literally, every time I do this, I take it, I just copy it, I paste it wherever it's going. Because what I'll do after I have this checklist in here, I'll go in here and for each of these bullet points, I basically add a note. So first one says, get familiar with the data. The data seems normal and I understand the parameters. Even though that's silly, in some instances, you're going to come across a data set that really confuses you. So if you are not familiar with the data, or you're not comfortable with the data, this would be your place to ask us questions. So maybe as a team, we're like, I don't understand how soil electroconductivity I can't spell, electroconductivity is measured. Okay, and so what that's going to do is provide whoever the team leader is or whoever's data set it is a piece of information basically saying, like, I could use some help here. And so hopefully whenever they receive your message or you send the document back and the data back, they'll go ahead and read through that and be able to provide you with an answer. Okay, so when I was talking about that in my lecture, I always put this data checklist at the top because it's just a nice, easy way to document what's happening across a team, especially in academia, where instead of being, software oriented or computer science oriented, we typically share things over email or over OneDrives or Google Drives, and after that, someone just gets left with a blank data sheet. Okay, and usually the biggest one is step number 5 here, because you'll just create a list of all the changes that have happened over the 3 or 4 versions of the data set that you're working with. So just like last time, we are going to start by getting into our virtual environment. We're going to practice our compartmentalization here. So for me, I know I'm in my base terminal here, just in P or Paul. I'm going to go ahead and go CD desktop because I know that I need to be on my desktop. And then I also know I have a teaching folder there. And then inside of my teaching folder, I'm going to go into my Spring 23 folder. All right, so we're there. We're going to list what's in that folder. I've got some documents. I need this DAT-SCI virtual environment. Notice how it's color coded it's in a different color than my regular forms. Okay, so this is the one I want. So if you notice over here on Windows, you're going to type in the name of your environment. Mine's DAT-SCI. /scripts /activate.bat. If you're on Mac or Linux, we're going to type source. If you can spell, we're going to type source DAT-SCI /bin/activate and go from there. And now notice that it pops up this DAT-SCI emblem, which basically is telling us that we are now in that data science environment. So this is essentially, think of it as a cube or a box that we're putting information inside of in here to access it only under specific conditions or parameters, which we have already established basically, right? Because we were talking about in our last class period the fact that we can specifically put NumPy and pandas in this environment so it does not cause global changes to our computer. Sometimes that's beneficial, sometimes it's unnecessary. In our case, it's just good practice to have those saved in a specific development environment. All right. If you haven't already, you need to install Pandas. That's as simple as pip install Pandas, which I've already done. So it's going to check that I've met my requirements. It says requirements already satisfied, and then it's going to move on. All right. So now we are ready to actually take a look at some data. So we're going to be working with a popular data set, and this data set is called Iris. Everybody can still see my screen, correct?
Yes, we could see.
All right, so this comes from R.A. Fisher. Fisher is a giant name in statistics as well as ecology. He invented many formulas that are still used to this day. This specific data set is incredibly well known. It's essentially, he went around and measured irises and measured certain attributes about the flower. So like the sepal length, the petal length, the sepal width, the petal width, and then he also measured for 3 different species: Iris setosa, Iris versicolor, and Iris virginica, excuse me. So this is basically that data set. This has been published since, I don't know, the 1970s, 1980s, right here. 1936 was the first time that it was published. So a very long time ago, and it was specifically in contributions to mathematical statistics. So that this is his specialization. And we use this all the time to teach data science. If you are ever interested in learning R, I would literally just Google Iris tidyverse, and a introduction to tidyverse packages specifically for R data science comes up using the Iris dataset. Like, this is the data set that we use to teach this specific skill. Also, if you're ever looking for other free and open source machine learning repositories, you can check out this website. It's in our file for today, but it's a machine learning repository where people post open source data sets, and you can also find publications to other machine learning data sets. So that's this link right here. So that's the data we're going to be working on today. And we're just going to hop right in. So let me back up, right? Because step 1 of our data set is to get familiar with our data. So we're getting ready to do this. So far, does everyone understand about what kind of data we're going to be looking at today? We're going to be basically examining or looking at the basics of the data for flowers for 3 different species, as well as 4 attributes of those flowers: petal length and width, and then sepal length and width. Does that make sense to everybody?
Yes.
Okay, perfect. So we will just go ahead and jump right in then. So I'm going to open up Python here in my terminal, and we are going to start working. So I'm going to go ahead and import pandas as PD. PD is the standard shortcut for pandas. It just saves you a little bit of time while you're typing. And then we are going to access this data set from that archive location that I just showed you. So we're going to type in CSV link, and then I'm going to copy this link over and paste it in there, load in that data. So now we have that data in there. And then I'm also going to create a new object in our data, or excuse me, in our environment called Iris. And Iris is going to consist of PD for pandas and then read CSV. So we're going to read the data set in from that archive location as CSV underscore link, comma, header equals none. And you might be asking yourself, why does header equal none? Well, because the data set that we just imported, if we pull up Iris, you'll notice that there are no headers in there. So this is an index-based data set. If you want the column names or the header names, you have to access them in a separate location and import them in. So that's what this next set of code does right here with the column names. So we're going to copy the column names over, paste them in. So now we've got column names saved as an object, and we'll recreate this Iris object. So we'll iterate over it, and we're going to say Iris is equal to PD dot read CSV of CSV underscore link, comma, and now names will be equal to our column names that we just imported. All right, and that worked fine. Now we're going to pull up Iris. And what you'll notice is we have our columns names now, right? So we've got over here on the left-hand side, we have 0, 1, 2, 3, 4, 1, 4, 5, 1, 4, 6, all the way to 150. Those are basically our row numbers, so our observation numbers. Across the top, we've got our column names: sepal length, sepal width, petal length, petal width, and then you see over here on the far right, we have species. So this is kind of not necessarily a unique setup, but it's interesting that the species is over here on the right side. Typically, when somebody is going to record a field observation, the species is going to be the first thing you're going to recognize in biology. So like if I was walking through a field and specifically looking for flowers, when I noticed the flower, I probably noticed it because I either know what it is or I know I need to key it out and figure out the species. So in my mind, that's already something I don't like. I don't like that the species is all the way here on the far right. I'd rather be over here, the very first column I see, but that's nitpicky. The important fact is here that we have gotten our data set loaded in from a URL posted online. It's visible. It appears to be in a format that we can work with. And so we are going to do step 1 of our data checklist and get familiar with our data here. And so let's go ahead and do that. So we're going to get familiar with our checklist, basically, or with our data, excuse me. So basically what this means is we want to understand all the variables and what the data set was looking at. All right, so we've already pulled up the data set here, but let's go ahead and just practice some of our functions. So we'll go iris.head. Remember that .head shows you the first 5 rows of your data set by default. If you want to show more than the first 5 rows, you can specify that. So I want the first 15, and you'll see it shows me the first 15 rows of our data set. Okay, so examining our data set, we'll notice that we have our same 4 columns of actual measurements that we've been looking at, and then our species. The species appears to be in what I would consider to be a unique format. That's because this is stored in an online database. So you'll see it's iris-setosa. That could get very confusing, or not confusing, but complicated to type in if you wanted to subset by just one of the species. So later on, we may actually practice reformatting this and removing the iris off of the beginning. We just want the setosa, or we just want the virginica. So we may make that change earlier. That's one of the first things I notice. Let's try iris.index, and it tells us our total range here. So we're starting at 0 and we're stopping at 150. So basically we have a range on this data set of about 150 observations. And each of those observations has 4 different measurements, or that's our assumption. Let's try iris.columns. All right, so we are going to look up our columns here. It says index. We have, and it's going to show us all of our columns. So we've got our 4 measurements and then our species, and it says data type is equal to object. That makes sense because we've stored iris as an object in our data, or in our environment here. Now let's try just sorting it. This is more of just an aside. This doesn't really tell us much about the data, but we're going to go iris sort values. And in this situation, we're going to specify the by as petal length, or excuse me, petal width. Make the assumption that is an attribute that provides us value in this situation. And then we're going to check out the top 10. Oh, not 1, 10 observations. All right. And notice it's kept its index position. So over here on the far left, we have random numbers essentially. We have 32, 13, 37, 9, 12, so on and so forth. But what it's done is taken the petal width and sorted it in what appears to be ascending value based on the petal width and possibly the species, or it's just possible that this species has the lowest petal width. That's more likely. To check this, notice that the petal length varies somewhat throughout here. It's actually still pretty consistent. Let's resort this by sepal length and see if that changes our view here. This is a curiosity just because of the, oh, that was a bad decision. Just because of what we see here, the fact that the petal width is all showing one species. So let's see if we change that Sepal length, is that not a thing? Or did I spelled length wrong. All right. There we go. Same thing. So it appears that Iris setosa is it's possibly our smallest species here. We could reverse this. So if we go back to petal width, I believe if we come in here and go descending equals false. Let's try that. Descending is wrong. Let's try ascending. And I don't remember how to spell ascending, something like that. There we go. So if we do the ascending values based on the petal width, so starting from the top and working our way down, you see we get the other end of the list. So it does appear that we have a species separation based on the petal width, which is kind of interesting. I wouldn't expect it just to be the petal width, but it's consistent, right? So on the low end for the sepal length, or for this, no, not the sepal length, excuse me, the petal width, you see that we have all the Iris setosas. And then when we reverse it and do ascending or descending, excuse me, we see that Iris virginica is the one that constantly shows up. So Iris setosa is apparently our smallest species, and Iris virginica is apparently our largest species. That's kind of interesting. So that's kind of typically my end to step one on our data checklist. I just want to get familiar with it and make sure I understand it. In this situation, I'm a biologist, ecologist, entomologist, whatever, by trade. So this data makes good sense to me. Is everyone else comfortable with it, or does anyone have any questions about this data set? Okay. I will take the silence as we are good to go. Step 2 here is to check for structural errors. So this is basically like, is all the data in the place that we want it in? As I was stating, sometimes people put things in weird places. So like an alternative format of this, let me see if I can, I'm going to switch to a whiteboard and go from there. So an alternative format for this data set, let's say we have each column being a species. So I'm gonna shortcut them. Hold on one second. Virginica, versicolor, I'm gonna call them color, virginica, and setosa. So we're gonna say we have, whoa, that's probably way too zoomed in. All right, let's fix that and then go back. All right. So we're going to say we have virginica, setosa, and then color. This is the only thing I can remember. So we could potentially have those as our columns. And then someone could have, for instance, recorded, we could have another column called observation, just like what number observation they are. So that could be 1, 2, 3, 4. And then our attributes that we're measuring, petal length, petal width, sepal length, sepal width, could all be the rows. So we'd have our measurements for each of these individual species based on observation running this way. And if someone handed us the data in this way, it obviously may be confusing. Maybe we're like, well, I don't know how to analyze this based on species in this format. And so maybe our preferred way to handle this would be to convert it into the format that we want, right? So if we're in this format, we essentially need to take these 3 species and turn them into this observation column, and then get rid of this observation column, and then take these rows and move them up into our column positions. Does that make sense to everybody? So we basically would have to do a full rotation of this data. We take all 3 of these species and then convert them into a column, and then move these rows into a column, and then take these observations and convert them into rows. And so the end product here would be exactly what we have right now. We'd have our observations as our first column, 1, 2, 3, 4. We'd have our petal length, our petal width, our sepal length, and our sepal width and then species is the last column, right? So this is the format that we're in right now. So if someone handed us the data in the other format, we would have to make all those conversions by hand. And so in step 2, let me get back to my screen. In step 2, that's kind of what we're checking for. We're checking to make sure the data is in a format, that a structural format that we are okay with. And in this situation, does anyone see any issues with how our data is set up? Is there anything we want to move? I'll take that as a no. And that's, oh, go ahead, Robert. What's up?
So we're looking at the data on the bottom right. So it looks like it's good there.
Yeah, I agree with you, Robert. I think in this situation, because we don't have a specific question, right, which is a failure on my part, not really, but kind of, right, because we're just doing an example. But because we don't have a situation or question that we were trying to answer that requires a different format, we are in the correct form right now. So the data was given to us in a way that we can work with. Okay. So then step 3, check for irregular formats. Now, this is where it can get complicated, because sometimes you want a specific format until you get to a certain position, and then you want to convert the formats. Some people prefer to do it all at the beginning. It really just depends on the person that's doing the analysis. But we can check our data types. So we're going to go iris D types. It's probably, there we go. So we can see that data type, overall data type is object, species data type is object, the others are float 64s. So when it says object here, it's basically telling us that it's text. So we might not, maybe we don't want that, maybe we do want that. At this point in time, it's kind of hard to tell. There's certain situations where having this, having letters in here, having text in here is really going to mess things up. Because the way that some people program is that they are only working with numbers, so they don't care what species it was. That species was an observation at a point in time and a place in time, and that point in time and place in time is the important part, not the species name. So there's certain formulas and equations and algorithms that are only written to work on numbers or certain data types. In our instance, in this case, what we're going to work on today, I don't think having that as an object is an issue. And also having everything else as floats makes sense because we have plenty of decimal points here. And that's because of the accuracy of our measurements in the field. So, okay, we're good. Now, number 4, decide what to do with your missing values. Are we missing any values? I haven't seen any evidence so far. And then if we are missing values, what should we do with them? In this instance, having 150 data points, that's actually pretty significant. Since we have 3 different species, we can make the assumption that we have 50 observations per a species. Which is actually really high in ecology or entomology, whatever subfield of biology you're in. Typically, you can get away and like find significance values down between 20 and 30 observations. You don't really need 50. So even if we had some missing values here, it would be okay for us to lose 2, 3, 4, 5 data points in this specific situation. But remember, it's all about your situational awareness, right? So let's see if our data set is missing any data points. So we're just going to go iris dot is null and then our parentheses. And you see that it's showing us all the way through false, which is telling us that there are not nulls in those positions. If we want to show the entire data set, we can, I think we can go into is null and say all. I think that's no, takes one positional argument. Let's just, the easy way that's coming to my head right now is just go dot head 150 and then it'll print, or it won't print the entire data set. So it doesn't want to save itself time. So we'll look at the top 15. We'll look at tail also. We'll do the bottom 25. And my assumption is, since this is saved in an archive, they would have deleted or gave us a note about the data. And just from having worked with this data set before, I am aware that there are not any missing data points, right? So that's kind of this is your time to find those. If you want to find them, you can use the is null, you can use drop in a, you can handle your missing data from the beginning if you want, or you can wait till you get further down the line and decide what to do with them. Because sometimes maybe you do have missing data, but the missing data will not affect one of your questions. So you have some observations you could keep in till, a certain point and answer a couple of your questions, and then you can denote in your methodology that, hey, to answer this specific questions, I had to cut my data set down to 14 parameters. So you just chop that parameter off. Whatever it may be, there's always a solution to work around missing data. Or you don't work with the data. And that's the unfortunate part, is sometimes people give up and like, well, it didn't work the way I wanted it to, so the data is gone, right? All right, so that's our data checklist. Okay, number 5 is document any changes made to the data and the project. From what I see in our data, I'm just going to leave a note and say the data appears cleaned, and organized in a way that the team can start making progress. All right, and that's good enough for me. Just a little note so that next time we come in here, we know what happened. Now we're going to start doing our normal Python type observations. I'm going to clear this real quick and then go back into Python. All right, so import. All right, so we are going to start accessing and slicing and dicing and working through this data. I might not, maybe I shouldn't have done that. I bet our data set isn't saved anymore. Yeah, iris is not in here, not defined. Hold on, guys. I made a silly move just because I wanted to clear my screen. But we can fix that. All right, and then we will come in here. Okay, there we go. So now we can see iris again. There we go. All right, so we can access this data just as we've accessed all of our other types of data. So we are basically going to go through here and use our square bracket notation to pull whatever data set or pieces of data out of here that we want. So for instance, I can go iris square bracket and then call on sepal length and close that off, and then go ahead and it'll show it to us. Unterminated string. I missed a parentheses. There we go. And it's just going to show us the top 5, but it's going to show us just the sepal length column, the measurements for the top 5 of them, and based on observation number, no other index. We can ask for specific rows within our data set using the square bracket notation as we practiced last week. So this one specifically asks from 0 to 20. We can do it the opposite. We could say from 20 to 150, right? So it's going to cut us off again, but we can start at 20 and work all the way to the end. We can ask for multiple columns at one time. This one sometimes, and I see now that I did it wrong right here. It's where I said selecting multiple columns. To be able to access multiple columns, you have to use double square brackets. So right here, this should actually be square bracket there, square bracket at the end of our words, and then another square bracket. And the reason for that is when we give the subset command with the square bracket, it is only expecting one word or one argument there. So you have to put it inside of another argument to be able to select that element that you are looking for. So we can type in here sepal length and then petal length. So basically, if we're making a comparison to them, and then close off with our double brackets, and there we go. So now we've got a column of all of our observations for the 2 specific columns or attributes that we asked for, and they're not ordered in any way. We could also add an ordering factor on there and ask it to sort these. So let's go back up and get dot sort values right there. So we'll do, yeah, let's sort by dot sort values. And then we're going to ask for by, and then pedal. We'll sort by pedal length. Why not? It's not hurting anything. Close that off. And there we go. So now it's sorted by pedal length from smallest to largest. And the sepal length observations, because we're specifically sorting by pedal length, will not, they will be in the correct place. They'll hold their position. They will not change and become uncorrelated with that same observation. So that's that. We can also select specific rows by specific columns. So for instance, if we were starting with this setup right here, we want to access the sepal length and the pedal length of the iris data set. I can also come in here and specify, say, colon. So I want to start from the beginning all the way to the 25th row and then run that. Oops. Int object is not subscriptable. Uh-oh. Do I have to, did I miss a quotation? No. Maybe I have to have the beginning object here. Oh, I know what it is. I forgot to put the lock. Lock is location. I now I see it. I am missing a very important comma in here. So if you read this statement, you see it's 0 to 25 and then directly into another bracket. That will not work. You need to do your comma here to separate your arguments in the lock. There you go. So now we have the first 25 observations for those two columns that we asked by. We can overcomplicate this again and go dot sort values or sort by, whatever the function is for this one. So you can combine all of these functions together. You can filter based on condition that you suggest. So we can use the filter function specifically that is built in to Python. So it's just filter. And then we're going to tell it what items we want it to filter. Items equals, and then same thing, sepal, we'll do sepal width, and then pedal width, and then square bracket, circle bracket, there you go. And so it shows you all those, except we are, why is it only showing me one? I'm not going to worry about this right now, but I don't understand. Did I miss something? Iris, filter, items equal, sepal width, pedal width. Let's look it up. So we'll go over here, that out of my way. We're going to say python.filter. Okay, everyone can still see. Python filter W3 schools. The filter function returns an iterator where the items are filtered through a function to test if the item is accepted or not. Oh, I got you. So what we asked here, and I didn't realize this when I wrote it, but what we asked here is we want it to filter these items. So we're asking it to filter by the sepal width, and the iterable is the pedal width. So, oh, and I also see that I have a typo. That may actually be what's holding us back here. There we go. It was just a typo, guys. So you can filter by multiple conditions. Some people find this easier. To me, 6 one way, half dozen the other. Most of the time I don't use the filter function, and that's because if I'm doing something like, oh, let's go with this. So we're gonna say I want to subset the iris data only for these two columns. Most of the time I'm turning that into another object. So I'm gonna say iris comma or underscore length, and I'm going to say that's equal to iris that. So now I have a second data set called iris length. That's typically how I use this. When I've decided I'm comfortable with my data, I do not typically use the filter function, but people that go back and forth between R and Python do find the filter function more useful. So if you learn that in the future, you may be interested in using it that way. Now we can filter our data set based on conditions. So like over here, what I have is that we want to filter the iris data set based on our sepal width being greater than 3.5 centimeters and our petal width being less than 0.3 centimeters. So if we just take those conditions there, and there's nothing special about what you write here. You're using the square brackets to subset again. So you do iris, and then within there, you're asking for iris and sepal width within iris to be greater than 3.5, and inside of your square brackets, and the iris petal length to be less than 0.3. So we can hit that, and it's going to provide us with our data. So we had 1, 2, 3, 4, 5, 6, 7, 8 observations that met our criteria. And notice how they all are Setosa, our smallest species, as we learned in our get familiar with our data set section. Okay, so we can subset that way. You can also subset by query, which is the same thing. It's the same thing as the filter argument, 6 one way, half dozen the other. So we can go iris query and then specify what we want to query. So we're going to go sepal width being greater than 3.5 and petal width less than 0.3. So in theory, assuming I wrote this correctly, we should get the exact same result. And we do. Same exact observations, same species, same measurements. So it works either way. Nothing's different. Now we can, as we were discussing the other day, or as I think I mentioned it in my lecture specifically, we can always check out the columns of our data. And in some cases, it's really useful to rename these columns. So in this example, we're just going to do iris.rename. And we're going to rename the species column to class. And the reason for that is just because this is an example. So in some instances, you may not like how the person that input the data input it. You may want to refer to things in a different way. So this is just the way to do that. So you go rename, and I put a space there. You do not need a space in your dot notation. Dot rename columns equal species, and you're using a key value pair here. So you're telling it when you find the species column, please rename it to this value, which in our case is class. And then we're going to do comma, and then we're going to say in place equals true. In place is referring to the position of that column. So in this case, we specifically told it to place the species column, the new column named class in the same position as the species column. If we changed in place to false, it would put it in a new column. You can also create new columns, and we'll go over that here in a minute. Now let's look at iris. You'll notice that iris now is called class. So it worked perfectly fine. We renamed it. It took half a second. Now, there is a more complicated path here where we can rename multiple columns based on a condition. I have, and I mean this seriously, I have never once done this, never in, let's see, 5 or 6 years of having to do statistics and data science stuff. I've never, ever done this. But the example is there, lines 142 to 148, if you ever need to do it. And I'm so confident you won't. We're not even going to go over it. It's literally not that important, unless you have a giant data set with hundreds and thousands of parameters, but I highly doubt that will be the majority of your situations. So now this is an example from what I was talking about earlier, right? So sometimes having a mixed type of data will prevent you from running your statistics or using certain algorithms or packages or whatever. So in this example, basically, we're going to go through how to convert the name or the value of a cell into a different value based on conditions. So we're using the same tools we've already used. We've already used this lock or LOC, and basically just specifies a location. So what this is saying is iris.lock, so the location, and then we're going to ask for the location of iris and then species. And that one, and then we're going to say that double equals to, we're going to change it specifically to the name Setosa, and then comma, And then we're going to say species and then close off our bracket. And we're going to make that equal to 0. Did I spell species wrong? Oh, species doesn't exist anymore because we changed it to class. Haha, that's funny. So we're going to go ahead and change that to class. And this one also should be class. Oh, of course, I'm fat fingered it. Let's see, there we go. All right, now let's look at ours. And that clearly did not work. So what did I type in wrong? So or maybe it doesn't work until you run all of them. Let's see. Oh, it's the species thing again. All right, well, let's change them. So that should be the format. I've done this before. I know that works. Part of the issue we may be having is because it's not reading. I should have changed the order of operations there. We should have done this rename after we did this change. So we could go back and fix that really quick. Let's erase all this and we will actually rename our old column back to species. So we're going to go columns and then say class is actually mapped to species again and close that off, comma, in place, true. And then iris. Okay, that's changed back to species. Let's see if that fixes my issues here. It did not. Let's keep going and double check that we don't have to submit all 3 before we do get the final updated version. We did not. Interesting. Okay, let's go to Magical Google. So we are going to come in here and say change cell value based on condition, Python, pandas. Pandas replace values based on condition. All right. So you can replace all values or selected values in a column of pandas database based on condition by using dataframe.lock, np, where, and dataframe mask. So we want to use dataframe.lock. So do they have their data set here? Let's see. I just want to see it. So we are not dropping. We're probably at the beginning somewhere. All right, so that's their data frame. And then we are good up to that point. We're on a subset based on condition. Let's see. So below are some, if you're in a hurry, below are some quick examples to replace column values based on the condition in the data in Pandas data frame. So that's probably our problem now that I look at it. Notice in our species column here, it says iris-setosa, right? I was talking about how I don't like that format earlier because it makes it hard to subset. Well, here's that exact example that I was discussing, right? Because if you look over here in our formatting, we have iris, we asked to access the species column within the iris data set, and then we're looking for the condition that exactly equals to setosa. Well, guess what? That doesn't exist. So what we may need to do here is come here and change this to iris-setosa there and try that on our terminal here. And now let's take a look at iris. There we go. So that works. So that's the issue. So that is why I do not like this format. It's incredibly hard to remember. And we just started working with this data set, right? It's not like I've been staring at it for days on end. I already forgot that that could potentially be the problem. So we just need to change this to match the format. And this again is sometimes why people prefer to only work with numbers, because if they are, you can always have like a little note sheet or text file off to the side that you may want to input. I don't think that changed both of them. There we go. Let's make sure this one reran. But you can always have that information off to the side that like 0 is equal to Setosa, 1 is equal to Versicolor, 2 is equal to Virginica. You could have that off to the side if you want, or you could just leave it as the names. But I would definitely recommend renaming from this format. That is just a rough format. So you can find and replace, and you do that by using the cell conditions, right? Because all we're specifying is the name here. So instead of turning it from Iris Setosa into 0, which now we're going to have a problem with, we could change it from Iris Setosa to we could suggest just Setosa. So now we're going to come in here and change this, and we'll revert this back to 0. And it's actually being read in as a number right now. So we can grab that and come over here and then paste. And then we can look at Iris, and now Iris just says Setosa. So it's not like this is hard to do. It's just a couple of steps. It's just, those little things and people's preferences. It all makes a difference. It all affects the way that you analyze the data, which can be frustrating. So now we're just going to go through some basic functions and talk about how to summarize it for the last 10 minutes or so. So we're first going to look at the length of the data. Let's say we just want a total count of how much data there is. We're going to go length of Iris, 150 observations. Okay, cool. Well, now let's summarize those observations by groups or species or whatever you want. So we're going to go Iris dot value counts, and then we're going to say species, which we still have as species. There we go. So it tells us type 1 has 50, type 2 has 50, Setosa has 50. And that's because I left as a mixed format here. So that's just for this example. I would never do that in real life. We would always, and actually here we can change it back. So now it says, just so that we can have a consistency here. So now it says Setosa, and then we'll come back over here. So now it's fixed. So now they're all zeros and ones. Okay. So we can also group by the number of records for each group. So it's the group by function. You tell it what column you want, which in our case is species, and then we're going to ask for the size. So it breaks it down just by those groups. Basically the same way to do different things again. We can summarize our data by column. This is in Python, it's .agg for aggregate. So gather all this data. So we're going to ask it to take iris.agg aggregate, and then we're going to tell it we want it to aggregate. So in this case, we want a mean, and then we also want the minimum value for every column. And square bracket, circle bracket, there you go. So it's telling us it's created new metrics, the mean and the minimum for all 4 of our values here. And then this species is just nonsense. So species being 1 means that there is an occurrence there. For species being 0, it's 0. And also that could be actually, now that I think about it, that may actually be a problem because we've converted that into a different type. So it's not categorizing based on actual species. It's reading that as a number that it needs to fix, right? So now we have an issue, right? While we were examining our data, we've introduced a problem, right? So this is why it's important to have your situational awareness in these situations. So in actuality, we cannot leave our data in the format that it's in. We are going to have to go back through here and fix my mistake. So we are going to go back up. And now where it says species, the value that's going to equal 0 will be equal to Setosa, which needs to be in quotations. There we go. We'll use this one again, where it says 1, we want that to equal Versicolor. Okay, and then we're gonna ask where it equals 2 for it to equal Virginica. Right, so again, I accidentally introduced an error by just showing you how to work with this data. And that's what we want to avoid for the rest of the semester, really. All right, and that did not work. I see it. We did this as text. It's not text, it is shown as a numeric value right now. So we can actually go with this one. We just need to convert this to a 1 and then convert this to a 2. Ooh, that's not correct. See, now guys, I've messed up everything. If we look up our data, and this is why you don't do this. If we look at our data, I've accidentally combined all of our 1s with our 0s. So there is no way to rebuild this besides to go in and reload our data. And I know that's annoying, but sometimes you mess up. So we have to restart this object. Let's check that it reformatted itself. It did indeed reformat itself. Now we are going to go down here and just to see if my prediction was correct earlier, we're going to ask for this aggregation variable of our mean and our min and see if the results are different, which I expect that they will be. Future warning, species did not aggregate successfully. If any error is raised, this will raise in a future version of Pandas. Drop these columns / options to avoid this warning. See, so again, we haven't even made it that far. All we're trying to do is summarize our data. And you see that we're getting errors by simply summarizing by a column or by a group. So we would need to subset this data even further just to get a mean value for each individual species. Or we'd have to reformat essentially to get a mean value for each different species. And these are things that you play with. You could literally play with this for hours on end before you find a setup that you like, sometimes days or weeks on end. And if that doesn't sound fun, I do not recommend data science as a career. But let's see. So let's fix this. Virginica. So let's try to run these couple of lines of code and see if that worked. All right, so we fixed that. Oh, I forgot I can't. For some reason, my shift enter has not been working, and that's not been fun. There's that one, and then we'll get the last one, and then we will rerun again to see if this fixes the issue, or not the issue, but our error. There it is again. So you never know. We would have to subset the data to figure out why it's throwing this warning. At least it's a warning, not an error. But it's calculating the overall mean and the overall min. And in theory, this mean technically should be correct for the entire data set because it's showing no species, which would indicate to me this is an overall mean. So it aggregated everything together for the entire data set and calculated a mean. What's weird to me is that the minimum is showing us a species, which I guess isn't necessarily weird because it's pulling one row out of the data that is the minimum value for the entire data set. But I find it unsettling that it has given us a warning, which is why we're working through this. So again, that would just be something that you have to confirm that those values are right before you go ahead and report them in a paper or a publication or something. Your opinion in this situation matters a lot, right? If you were going to publish something as scientific proof or as data and make a suggestion for a hypothesis or research that you've been working on, you want to make sure you're correct. You don't want to have to ever withdraw anything. You don't want anyone to question, what is that called? You don't want anyone to question your legitimacy, basically, or you want to create legitimacy for yourself. So, you just have to be careful of these things. That's why it's important to take it step by step and make sure you're comfortable. So Now we're going to talk about real quick adding and deleting columns. So adding a column is as simple as saying, Iris, and I'm going to say, we're going to call it petal two, and then we could just literally make that equal to Iris and then call it petal width. So you can create an entire new column based on an old column if you really want to. It doesn't matter. You can just specify these things to be added into your data frame. So in this instance, this is a silly example. I'm just doing it so that we have an example. Okay, and then let's check out Iris. And you see Iris now magically has a new column called petal 2, which is equal to the petal width. So petal 2 is the petal width. We've just added it in there and pulled the values over and copied them, right? And so you can do that for any observation you want. So we could take this petal width and go divide it by 2. And so now it'll take all of those Iris 2 values and divide them in half, right? So we've just arbitrarily added a metric in there. Now, most of the time when you're doing this, you're creating a column for percentages or proportions or whatever metric you may be interested in that was not given in your data. Or you could take the mean of something and store of that observation and store that in that column. You can specify all that at your own will. If we wanted to get rid of this, all we're going to do is iris.drop, and we are going to tell it what to drop. In our case, petal 2. Not found in axis. I believe axis is equal to 1. And so I guess I did write it correctly. And then in place equals true. There we go. Now let's look at Iris, and petal 2 is gone. We're back to our original data set with our corrected species names. So overall, Pandas is not hard to work with, guys. This is fairly easy and should be fairly easy to pick up on. So where we go from here basically is we're going to take this data set and start to analyze it. We're going to look for correlations. We're going to look for hypotheses that we can test. And that'll be what your first actual homework is. That'll be the homework that is due on the 8th, as in next Wednesday. You'll have a homework assignment where basically I'm going to give you a question, potentially over this data set, potentially over a different data set that might be slightly more complex. You're going to have to manipulate the data into a format that is usable, or make sure it's usable. And then you're going to have to run a simple statistic. And that simple statistic will be things like the mean. It'll be things like the hypothesis test, and all the information will be there. So that's what I was hoping to cover today, and we got through it. Does anyone have any questions for me? Going once, going twice, sold. All right, so no questions. Just remember that your first homework, the GitHub profile, is due today. So please send that to me in Discord or over email. Your second homework will be out in the morning, and it will be, like I just said, it'll be you going through a data set and performing simple manipulations and gathering simple statistics. And that will be due on February 8th by midnight. So last chance, any questions? Okay, perfect. Thanks everybody for being here. If you do end up coming up with any questions, feel free to send me a message or an email, whatever works. And I hope you guys have a great rest of your week, and I will see you next time.
Hey, Paul, while doing the